Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 23, 2026, just 2 days ago. It introduces a framework that achieves up to a 47% relative improvement in recommendation accuracy by effectively solving the problem of latent drift during multi-step reasoning. The paper is titled, ManCAR Manifold Constrained Latent Reasoning with Adaptive Test Time Computation for Sequential Recommendation. And as we'll see later, the results are really impressive, particularly how the model learns to stop its reasoning process at just the right moment. And for those interested in the implementation, the authors have shared their code on GitHub. To visualize the core problem, Figure 1 illustrates the concept of latent drift. Notice the red dashed line representing unconstrained reasoning. It starts at the blue dot but eventually wanders off into empty space, completely missing the target. In contrast, the black path shows the ManCAR approach, which hugs the surface, or manifold. This path is guided by the orange squares, representing graph neighbors, ensuring the model stays within a feasible region and successfully navigates to the gold star, the target item. Figure 2 provides a blueprint of the ManCAR framework and its reasoning loop. On the left, we see how the model derives context from the global interaction graph, identifying neighbor items that surround the user's recent actions. This context enters the sequential recommendation model at the bottom to initiate the reasoning process. As the model generates intermediate states, the teacher prior in the upper right guides them, ensuring they align with valid item clusters rather than drifting off. To maximize efficiency, the adaptive halting component on the far right monitors the output and terminates computation as soon as the result converges. To evaluate performance, Table 1 details the 7 datasets selected from the Amazon 2023 reviews corpus. These cover diverse domains like CDs, office products, and grocery. The scale varies significantly. For instance, the grocery and toys datasets each contain over 2.5 million interactions. We also see differences in data density, where the average interactions per user range from about 9 in the office dataset to nearly 27 for CDs, ensuring the model is tested under various conditions. Well, Table 2 presents the head-to-head performance comparison across these 7 benchmarks. The central columns list standard baselines like SAS-REC and BERT4-REC, alongside stronger recent methods like GLAIRS. ManCAR, shown in the column towards the right, consistently achieves the highest scores, which are marked in bold across every single dataset. For example, looking at the CDs category at the top, the model delivers a remarkable 47% relative improvement in NDCG at 10. The final column quantifies this uplift, showing significant double-digit gains in almost all cases. So, having established that the model works, Table 4 asks which parts are doing the heavy lifting. This ablation study strips away features one by one to measure their individual impact. The most dramatic drop appears in the second row, labeled without teacher prior. Losing this guidance causes performance to plummet, confirming that the manifold constraint is the core driver of success. The third row shows that removing the context also hurts, while the bottom rows validate that technical details, like norm rescaling and loss schedules, are vital for stability. So, while Table 4 confirmed that the components are necessary, Figure 6 reveals the actual dynamics of the reasoning process on the circa Ds and video datasets. These charts plot the KL divergence, which measures how much the model's prediction changes from one step to the next. You can see a sharp drop immediately after the first step, meaning the model converges on a stable answer very quickly. By step 3, the line flattens out near 0. However, notice the slight uptick at step 5. This hints that reasoning for too long can actually reintroduce instability, which justifies the use of adaptive stopping to terminate the process at the perfect moment. Wrapping up, 2 key takeaways stand out. Treating recommendation as navigation on a constrained manifold effectively eliminates latent drift, and adaptive stopping ensures the model is both accurate and efficient. This proves that grounding latent reasoning within a global graph structure is a powerful recipe for next-generation recommenders. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.